Hello everyone, welcome to section 7.6 on molecular structure and polarity. We will be covering this section in a series of short videos. In this first video, we will cover the learning objective of predict the structures of small molecules using valence shell electron pair repulsion theory. Let's go ahead and get started. So as we've talked about molecules, we have used the Lewis structure notation, and your book is talking about this as a two-dimensional representation. The Lewis structure itself is not meant to be showing a shape or anything of that nature. It's meant to show how many bonds you have. So a lot of the misconceptions related to Lewis structures and shapes are because Lewis structures are not meant to indicate a shape. So there's a lot of information, if we care about the shapes of molecules, that is not included in a Lewis structure. But as it turns out, we can use Lewis structures to figure out the shapes of molecules. They're just not exactly the same thing. So in order to properly describe the shape of something, we need some information like bond angles and bond distances. So we're showing an example here. So this looks like kind of like a Lewis structure, but we're saying more specific things here. This is the angle of this bond is in this particular case, 118 degrees. This is the length of this bond, 1.21 angstroms. We're not going to get too deep into the bond lengths in this course, although that is certainly something that could be looked at in more detail. So how we go about using the Lewis structure format to come up with the shapes of molecules is something called VSEPR theory. So valence shell electron pair repulsion theory. And this sounds like a lot of really big words, but it turns out you already know what they all mean. So the valence shell electron pair, that is the Lewis structure itself. So when you draw a Lewis structure, you're showing the pairs of electrons, and that's all we care about, is those pairs of electrons. And then the other big words are our repulsion theory. So the idea is that to have the best approximation of the shape of a molecule, what we want to do is we want to take all of those electron pairs and separate them as much as possible. Okay, so we want to get the electron pairs that we're showing in a Lewis structure as far apart from each other as we can. And if we do that, then we have legitimately predicted the shape for the molecule. A couple of things I want to highlight here as we talk about this. When we talk about these electron pairs, it could be any of these things that we're highlighting here. So they could be bonding pairs of electrons or lone pairs of electrons. Those bonding pairs could be in either single, double, or triple bonds. So we treat, in terms of looking at predicting the shape, we treat double bonds, triple bonds, and single bonds as being essentially the same thing, as a place where there are electrons. So let's look at an example. So here we're showing the Lewis structure for BeF2. And in this molecule, you have a central atom that only has two places with electrons. It has, again, this is one that doesn't follow the octet rule. It has, these two single bonds. And the best way to get two single bonds, or two, I shouldn't even say single bonds here, two places with electrons. So two places with electrons as far apart as possible, because in some cases these could be double or triple bonds. That to get them as far apart as possible, we have a line. So a 100-degree angle between the electron pairs. Okay? So we call this a linear geometry. Linear meaning that we have a line separating the pairs of electrons. We'll look at a few different possible geometries here. linear is the simplest one. Okay, so two regions of electron pairs. We have the linear arrangement that we're showing there, and we'll look at this table to kind of go through these possibilities. So linear is the first one. The next one we're showing here is three regions of electron density. And we're showing an example here. So a Lewis structure, this one is not following the octet rule. There are some that do follow the octet rule, but in this case we are not. And so the best way to get three things apart from each other is basically with a triangle. So we have 120 degrees between each of these. And I'm going to scroll down here. I think, yeah, so we do have the name there, is trigonal planar for that geometry. I think I will leave the table like this so that we do get the name of the shape. Okay, so three places is trigonal planar. I know you can't see all of this up here, but we do see the example. We have 4 places here. Okay, so 4 places is what we call a tetrahedral shape. Now, when we get to this shape is actually very important, because if you think about the octet rule, you will often have situations with 4 places with electrons that will come up quite a bit. So this might be the most important of them. And there are, as we'll see for many of these, there are several what we might call subshapes based on having maybe some lone pairs in some of those locations. One other thing to be aware of that is very important for the tetrahedral shape, unlike these two shapes, the tetrahedral shape is not a 2-dimensional shape. It is a 3-dimensional shape. We can't actually fit it onto a page. So what we're doing here is we're using something called the line dash wedge notation. And in this notation, we attempt to show a 3-dimensional shape by indicating when we have bonds that are not in the same plane as the rest of the shape. So to start with, we have bonds that are in the plane. So these 3 bonds, or these 3 atoms, are all in the same plane. So imagine them as the screen of the computer that you're watching this on right now. These are all in the plane of that screen. And then we have these other ones that are not in the plane of the screen. So this one that has the wedge is indicating that this is sticking up towards you. So sticking out of the screen towards you. And then this one that is indicated by a dash is indicating that it is sticking back behind the screen as if it's inside of the device. So the wedge dash notation is our way of indicating when something is 3-dimensional, how we can show that easily without becoming art majors. So on a tetrahedral shape, the angles are all going to be about 109.5 degrees. And this is showing a bit of that spatial arrangement. Although again, it is 3-dimensional, so just kind of be aware of that. This is one that often does get confusing with the Lewis structure format, because when you draw the Lewis structure, it looks like they're all 90 degrees apart, but that's not true. So just be careful with that. So for things that follow the octet rule, they will either be linear, trigonal planar, or tetrahedral. So we are going to talk about these other ones, but before we do, I want to focus a bit more on these 3, because these are the ones that will be most important to us, because they're the ones that follow the octet rule. And the first thing we want to look at related to that, actually the main thing we want to look at, is understanding 2 types of geometries here. So we can talk about what we've been looking at so far. We might refer to as the electron pair geometry. So this is counting all of the electron pairs on those central atoms, both bonding and non-bonding. But we have another type of geometry we care about related to the structure of the molecule. So in your book, they use it looks like they're using the term um, the molecular structure of the molecule. So let's look at some examples of this. So here we're showing a tetrahedral methane molecule, again using the line dash formation. So the shape of this is basically tetrahedral. However, we have another molecule we're showing here, which is NH3. And it turns out that for NH3, it also has the same tetrahedral kind of shape that the CH4 does. However, the way it works out is that one of those electron locations is a lone pair of electrons. There's not an atom there. It's a lone pair of electrons. So we have with NH3, we have the nitrogen, and we have 3 places with atoms, and 1 place where there's an electron. And we're not showing that electron here. But you can see how this shape is different than the trigonoplanar shape that we talked about earlier. This is not in a plane. These are not in the same plane. They're in different planes. So it has a different shape. And in fact, we have a name for this shape. This is called a trigonal pyramidal shape. Let me see if I can highlight that down here. So trigonal pyramidal is when you have a shape that is overall tetrahedral, but has 1 lone pair of electrons. Okay. It turns out we're showing the angle here is a little bit smaller. That's not something that I'm going to focus on too much in this course. But the way that works is that the electrons end up taking up more space. So the angles everywhere else are a little bit less. Again, we're not going to focus on that too much. Okay, so this is talking about how there's some differences in terms of the size and space that things occupy there. Here we're showing some other possibilities. Okay, so it turns out for trigonoplanar, we can also have a lone pair. And when we do, we then have what we call a bent shape, sometimes called an angular shape. With tetrahedral, we have kind of the regular tetrahedral, the trigonal pyramidal that we just looked at with the ammonia. And then also we can have a bent shape. And for this, so here we have 2 lone pairs, and then we end up with a bent shape. So the main thing you want to realize here, so that these are both, they both have the same name when we say bent shape, but the angles are different, right? So a little bit less than 120 versus quite a bit less than 109. Okay, so the angles are different even though the name is the same. So just be aware of that. And that the angles are kind of shrinking a little bit. You don't have to know exactly, that this is 106.8 or this is 104.5, but that they're just going to be a little bit less than 109. So those are some of the things you want to know related to shapes of molecules that follow the octet rule. I want to go back and talk about these other ones that don't follow the octet rule. Okay, so there's a couple of other shapes that are possible. This one and this one. So just by inspection, you can tell that the central atom for each of these has more than 8 electrons. So again, these are not following the octet rule, but they do happen, and so we have some names for these particular shapes. So this one with 5 groups of electrons around the central atom is called trigonal bipyramidal. And this shape is a little bit different than all of the others in that there are not going to be equivalent things. So for the tetrahedral and for the trigonoplanar and for the linear, they're all essentially equally separated. For trigonal bipyramidal, they are not. Okay, so not all of these locations are the same. and it turns out that that will affect some of the chemistry of things that have this shape. Not something we'll get into in detail in this course, but you might touch on in the second semester if you take the second semester. So in these shapes, we have essentially a plane where you have three of the atoms are in that plane. So similar in a way to the trigonal planar, we have a plane with three things connected to the central atom in that plane. And then we have something above that plane and something below that plane. So here we're showing it again with the wedge and dash. So the wedge sticking out towards you, the dash sticking out behind you. So if you were to kind of look at this in the plane that these three are in, these would look like they were kind of one's in front and one is directly behind the other one, and then bottom and top, and then one over here. So with this arrangement, we have within that plane, we have an angle of 120 degrees for each of those, but from the plane to above or below, the angle is only 90 degrees. Okay, so the angles here are different. So that means some of these are closer together than others. And again, that's where that will affect the chemistry. So we have different names for those. So we call this equatorial and axial. So equatorial are the ones that are sticking out, and then axial are the ones at the top and the bottom. Again, we can have those different names because they are not equivalent to each other. And then the final shape we have is the octahedral shape. This one, they are all equivalent, and they are all are going to be 90 degrees. Okay, so we have basically each of the different, X, Y, Z coordinate system axes. You have an atom located along that. So, two on the x-axis, two on the y-axis, two on the z-axis. Again, I'm not going to care that you know which axis is which for this course, but that's how we get to 6 things around that central atom. You'll notice that in this table down here, we have specific other possibilities for when we have 5 things. Okay, if we have something in each location, trigonal bipyramidal, but if we have lone pairs, we have these other possibilities. Same thing for octahedral. We have something in each locations, but we have some possibilities where we have lone pairs. I'm not going to care that you remember all of these possibilities, just for the ones that don't follow the octet rule. So just basically know the main options here, but do know the kind of the possibilities for the ones that do follow the octet rule. Okay, so let's talk about how we can then predict the molecular structure for these based on the Lewis structure. So you have to start with the Lewis structure itself. So if you're just given the formula, first go ahead and write the Lewis structure. And then count the places with electron density. So you would count both lone pairs and bonds around the central atom. When you do this, you're counting single bonds, double bonds, and triple bonds the same. They each count as one place. Lone pairs also count as one place. Identify the electron pair geometry based on the regions with electron density. So you have your options here are linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral. So using this chart we had looked at, so the number of regions 2, 3, 4, 5, or 6. So what you're basically doing here is you're looking at this as your kind of your answer for that. So what is the electron pair geometry? That will determine the angle of the bonds. Okay, will be determined by that. So that was step 3. And then we use the number of lone pairs to determine the molecular geometry. So in this case, if you don't have any lone pairs, the molecular geometry and the electron pair geometry are going to be the same. If you have some lone pairs, then we have those additional shapes that are possible. So the bent shape or the trigonal pyramidal shape. And again, there's lots of other shapes possible for the trigonal bipyramidal and the octahedral, but we're not going to focus on you memorizing all of those options, although a few of them might show up on the homework assignment. Okay, so some examples here of practicing this. Make sure you feel comfortable with that, with this idea, before we move on to the next concept, which is talking about molecular polarity.